All right, any questions here? Yes?
So this method limited to meshes which has like an even size of the even?
Yeah, this particular code is restricted to meshes that has an even like 2 to the n type of grid spacing. So if you don't have that grid spacing, the interpolation function both from find to cos and from cos to find is going to be much more complicated. So you need to figure out if I have odd numbered grid spacing, what is exactly my Coser grid, right? Should I have a spacing of 3 at some point? Like exactly what is your Coser grid? And then the interpolation functions is not gonna be a few lines. Yes?
Here your Coser grid is half the resolution of your...
Yes,
does
my
it make
Coser
sense
grid.
to go even coarser or...
Oh, so does it make sense to go even coarser? Yes, but I think most of the multigrid I see goes coarser by a factor of about 2. Right, of course if you have, as you said, an odd number of grid points, it's impossible to go exactly 2. Or if you have unstructured grid, it's impossible to go exactly a factor of 2. But like, I think most of the practice are going roughly a factor of 2. Any other questions? Yes?
I was curious to know if there's a way to find out maybe analytically how many iterations of smoothing are required at the beginning to really aid.
Yeah, there is not a lot of research done on that, and that number differs for different, not only for different equations, but also for different smoothing methods and different type of grids. So we are not going to go into that, but like not having enough smoothing is one of the primary source of possible multigrid not converging. Because if this is not enough and you still have some auxiliary components in the solution area, think of what this interpolation is going to do. It's not going to do a great job. Right, taking this, for example, interpolation from find to cos, if this R is very oscillatory, then just taking these values is going to get you a pretty bad approximation of this R, and you, as a result, garbage in, garbage out, you get a pretty bad approximation of the E. Yes.
So in some cases, if you have a very, very large set that you're working with, sometimes you maybe put more computational costs on the smoothing in order to then, instead of having the number of points, maybe divide by 4 or more to make it even coarse as far as the coarseness of grid is concerned. Are those two, can you play between those two?
Yeah, you can probably play between these two, especially if the interpolation operator is expensive, then you may want to do a fewer interpolations at the cost of doing more smoothing. Any other questions? Okay, so we haven't done the last component of this multigrid cycle is post-smoothing. So paste the pre-smoothing here, and U next is equal to U. All right, that completes our multigrid function. So let's test it. Oh, in your projects, don't submit your code without testing. Some of the function submissions I got obviously hasn't been tested. There are typos in the code. You run it, comes error, undefined function, whatever. That's like obviously not tested code. If you test yourself, you're going to see the error and you won't submit it. So please make sure you test things thoroughly before you submit it, because we are grading by using computers, not because we don't have people to grade it by people, but like it's the code you write is going to be read by computers, should be readable by computers. Otherwise, it's not a functional code. Yes.
Are the reports being human graded?
Oh, the reports are human graded, of course. Yes. But the code is not. Yes.
How do you choose a good value for gamma?
How do I what?
A
good value for gamma?
How do I choose a good value for gamma? That's a good point. We are going to discuss that next lecture. So a good value for gamma is trying to reduce the let's see.
Because if gamma is too small, then we don't progress.
Right. If gamma is too small, you don't progress very fast. So the good gamma is trying to reduce the components of the solution error that cannot be solved in a coarser grid as fast as possible. So if your coarse grid is a factor of 2 smaller, then what you should be doing is look at the eigenvectors of the iteration matrix R and look at what are the eigenvectors that cannot be represented on the coarser grid, that are too oscillatory to represent on the coarser grid. And then you should scale these R appropriately so the eigenvalues correspond to these, I should call fine grid eigenvectors. They should be reduced as fast as possible. So this analysis we are going to do next lecture. Yes?
I'm just curious, when we do the mapping, don't some eigenvalues go to 0, and so you would lose the information with those eigenvectors?
Oh, if I get an eigenvalue equal to 0, I would be extremely happy. So if I get an eigenvalue mapped to exactly 0, let's say here, that means the corresponding component of the solution error is get annihilated with one iteration. I would be happy for that.
And so when we chose 0.5, that meant that the -1 was mapped to 0. And so
Yes, right.
in that case, we solved it with cross-sector iteration.
Yeah, we solve the component of the solution error corresponding to that eigenvalue with one iteration. But there are many other components that I need more iterations. So for example, for this particular equation, this Jacobi iteration, it turns out the eigenvalues in this range cannot be supported by the fine grid, by the coarser grid. So it turns out, I think the optimal value of gamma is something like 2/3 or something, so that this thing is going to be mapped into a region that is kind of centered around 0. If you are centered around 0, then basically this part gets reduced as fast as possible. Okay, I think, does that answer your question? Okay, so let's test it. I think we still have some time for that. And let's, for example, U equal to multigrid U and B. Oh wow, that didn't produce an error. I'm surprised. Okay, so we did one multigrid iteration. Let's see. I am sure of U. Wow, that's pretty good, right? Just a one multigrid cycle. Let's start from 0. Let's actually start from 0 to actually see how good we are. 0's n plus 1. That's much better than like a lot of iterations of Jacobi, right? I mean, for the Jacobi iterations, we waited for way longer than that, and we just got a contour. Okay, and let's see the solution error. Minus U. I don't know. Let me do an absolute value of that. Well, do you see anything? I mean, I see something. Let me bump it up by a factor of 10. Yeah, something like that. So we still get some solution error, okay? And then let's do iteration again. Multigrid of U and B. Maybe again. Okay, then let's look at the solution error again. Okay, now times 10 is not enough. Times 100. Still don't see anything. Times 1,000. I see something now. Times 10,000. All right. So yeah, so multigrid is pretty good at solving linear systems like that. So when you go to coarser grid, you spend much less time doing one iteration, and the iterations actually converges much faster because again, we're going to do the analysis next lecture, but like if you're having a coarser grid, the range of eigenvalues are becoming narrower and narrower. You are getting away from the ones and minus ones. So the iterations actually converges themselves much faster. Question?
Yes, is MATLAB, what is doing MATLAB to solve, if we have big matrices, and we would like to solve a linear system, is MATLAB doing this kind of iterative methods or other iterative methods?
No, MATLAB doesn't have multigrid because multigrid really depends a lot on the type of differential equation you are solving. So if you think of multigrid, it's not a method for solving a linear system, really. If you just give me a matrix and ask me to solve it using multigrid, I have no idea because I need a coarse grid operator, right? And the coarse grid operator is actually a coarser discretization of the same differential equation. I cannot just take a matrix and just apply multigrid on the matrix. I need a continuous version of the matrix in order for me to know how to solve the error equation on a different grid. I need the concept of grid, and I need the definition of what is the same operator on different grids. So MATLAB has no way of implementing a multigrid as something like a backslash. Actually, backslash only solves things directly. There is no MATLAB wouldn't decide to do an iterative solution for using backslash. There are functions in MATLAB. You can do you can have things like conjugate gradient, min res, things like GMRes and things like that. These are more advanced iterative methods than Jacobi iteration. You can use, but MATLAB wouldn't automatically decide to use them if you just do backslash. You have to call them explicitly. Okay. Any other questions? No? Okay. Anshu is going to have an office hour Wednesday at the same time, so there wouldn't be any lecture. And I will see you next Monday.